For nearly a century, quantum mechanics has produced predictions so accurate that no experiment has ever demonstrated the theory to be fundamentally wrong. Its equations govern the behavior of every atom, every semiconductor, every laser, and every electronic system modern civilization depends on. The mathematics is extraordinarily successful. What remains unresolved is what the mathematics is actually describing. At the center of this problem is the double-slit experiment, a deceptively simple test that repeatedly forces matter to behave in ways that defy classical intuition. Electrons, photons, atoms, and even large molecules do not travel like ordinary particles when unobserved. They evolve as distributed quantum states capable of interfering with themselves across multiple possible paths simultaneously. Yet measurements always return a single, definite outcome. For decades, physicists have argued over what this means. Some interpretations invoke hidden variables or wave function collapse. Others accept the equations exactly as written and arrive at a conclusion that is far more disturbing. Reality may continuously branch into parallel worlds. The single experiment that split physics in two. In 1801, Thomas Young directed a beam of light through two narrow slits cut into an opaque barrier and observed what appeared on a screen behind it. What he saw was not two bright lines corresponding to the two slits, which is what you would expect if light were a stream of particles traveling in straight lines from source to screen. What he saw was a pattern of alternating bright and dark bands spread across the screen, an interference pattern, the signature of waves. Where the peaks of two waves arrive at the screen simultaneously, they add together and produce a bright band. Where a peak from one slit arrives at the same moment as a trough from the other, they cancel and produce a dark band. The interference pattern was unambiguous evidence that light behaved as a wave, and Young's experiment was immediately understood as a decisive demonstration of the wave nature of light. That understanding held for a century. Then the photoelectric effect complicated it. In 1887, Heinrich Hertz observed that ultraviolet light striking a metal surface could eject electrons from it, and subsequent experiments established that the energy of the ejected electrons depended not on the intensity of the light, but on its frequency. Brighter light ejected more electrons, but not faster ones. Higher frequency light ejected faster electrons regardless of intensity. This was inexplicable if light were a continuous wave. A wave of greater amplitude carries more energy, and a more energetic wave should eject faster electrons. Albert Einstein explained the photoelectric effect in 1905 by proposing that light consists of discrete packets of energy, quanta, each carrying an energy equal to Planck's constant times the frequency. The energy of a single quantum, now called a photon, determines how fast an ejected electron moves. More photons means more ejected electrons, not faster ones. Einstein received the Nobel Prize in Physics in 1921 for this work. The difficulty was immediate and obvious. Young's interference pattern required light to behave as a wave. The photoelectric effect required it to behave as a stream of discrete particles. Both results were confirmed and reproducible. Both could not simultaneously be true within classical physics, where waves and particles are categorically distinct kinds of things. This was not a problem that a minor theoretical adjustment could resolve. It was a fundamental contradiction at the heart of the description of light, and it took the full development of quantum mechanics through the 1920s. This was inexplicable if light were a continuous wave. A wave of greater amplitude carries more energy, to provide a mathematical framework that accommodated both observations without resolving the contradiction in classical terms. The resolution that quantum mechanics provides is not a synthesis that explains how light is simultaneously a wave and a particle in some deeper sense. It is a mathematical formalism that correctly predicts the outcomes of both experiments while providing no classical picture of what is actually happening between the preparation of the experiment and the observation of the result. The wave in quantum mechanics is a probability wave, a mathematical object called the wave function, whose squared magnitude at any location gives the probability of finding the particle there if a measurement is made. Between measurements, the wave function evolves according to the Schrödinger equation, which is a wave equation. It produces interference. It spreads out in space. It passes through both slits simultaneously. When a measurement is made, the wave function appears to collapse to a definite value at a specific location, and the interference pattern disappears. This collapse is the source of the problem that has occupied the foundations of physics for the past century, because the Schrödinger equation itself contains no mechanism for it, and no one agrees on what it means. The double-slit experiment makes this problem concrete in a way that no abstract formulation can match. Send electrons one at a time through the double slit. Each electron hits the detector screen at a single point. Over thousands of electrons, those points accumulate into an interference pattern, the same pattern that would result from a wave passing through both slits simultaneously. Each individual electron produces a single, localized hit. The full sequence of electrons produces a distributed wave pattern. Somehow, each electron, traveling alone, with no other electron present to interfere with, passes through both slits at once and interferes with itself. The interference pattern is not produced by electrons interacting with each other. It is produced by each individual electron existing, in some sense, in multiple places simultaneously, until it hits the screen and is detected at one of them. Richard Feynman, in his lectures on physics delivered at Caltech in the early 1960s, said of this experiment that it contains the only mystery of quantum mechanics, and that anyone who claims to understand quantum mechanics without feeling confused by it has not understood the question. What a particle actually is before you look at it. The quantum mechanical description of a particle before measurement is given by its wave function, a mathematical object denoted by the Greek letter psi that assigns a complex number to every point in space and every moment in time. The physical content of this wave function is, in the standard interpretation, probabilistic. The squared magnitude of the complex number at any location gives the probability of finding the particle there if a position measurement is performed. The wave function is not a description of where the particle is. It is a description of where the particle might be found, weighted by probability. This probabilistic interpretation, proposed by Max Born in 1926 and now called the Born rule, is one of the most precisely confirmed rules in physics. It predicts the statistical distributions of measurement outcomes across an enormous range of experiments with accuracy that has never been violated. The problem with it is not empirical. The problem is conceptual. The Born rule is a rule about what happens when a measurement is made, and it says nothing about what the wave function represents between measurements. Born's interpretation treats the wave function as a catalogue of probabilities, not as a description of physical reality. But then the question arises, if the wave function is not real, what is? And if it is real, what does it mean for a particle to have a definite probability of being in two different places at once? The wave function of a particle in the double-slit experiment, after passing through the barrier with two slits, is a superposition of two components. One describing a particle that went through the left slit, and one describing a particle that went through the right slit. The word superposition is the technical term for a quantum state that is a combination of two or more distinct classical states. In classical physics, a particle goes through one slit or the other. In quantum mechanics, the wave function for a single particle going through a double slit is a sum of both possibilities, simultaneously. This superposition is not an expression of ignorance about which slit the particle really went through. It is the actual quantum state of the particle, and it has physical consequences. The two components interfere with each other on the far side of the barrier, producing the alternating bright and dark bands of the interference pattern. The reality of superposition becomes most uncomfortable when it is extended beyond the position of a single particle to properties that seem more definitively classical. Electron spin is a quantum mechanical property with no classical analogue, an electron can be in a superposition of spin up and spin down simultaneously. When the spin is measured along a given axis, it always gives a definite result, either up or down, with probabilities determined by the wave function. Before measurement, in the superposition state, the spin is not up and not down. It is not that we do not know which it is. The electron demonstrably has no definite spin along the measurement axis before the measurement is made, because if it did, certain interference experiments that can be performed on electrons in superposition states would give different results than they do. This was not a theoretical prejudice. It was demonstrated experimentally by Alain Aspect and collaborators at the Institut d'Optique in Orsay in 1982, in a landmark series of experiments testing Bell's inequalities. John Bell had proved in 1964 that any theory in which particles have definite values of their properties before measurement, what he called a hidden variable theory, must satisfy a set of statistical inequalities when measurements are made on pairs of entangled particles. Aspect's experiments violated those inequalities at statistical significances exceeding 5 sigma, confirming that no hidden variable theory of the local classical kind can reproduce the predictions of quantum mechanics. The particles in his experiments did not have definite polarizations before measurement. The measurement itself, in some sense, determined the outcome, and the outcome at one detector was correlated with the outcome at the other in ways that could not be explained by any pre-existing shared property. What a particle is before you look at it, therefore, is not a question that quantum mechanics answers in classical terms. The wave function describes a state of superposition across multiple classical possibilities. The particle does not have a definite position, or a definite spin, or a definite polarization until a measurement forces it into one. The question that has divided physicists since 1926 is what that absence of definiteness means. Whether it reflects a genuine indeterminacy in nature, a limitation on what can be known, or whether the wave function describing a superposition is a literal description of a particle that exists simultaneously in multiple states, in multiple worlds. The mathematics that predicted everything and explained nothing. The mathematical formalism of quantum mechanics was assembled across roughly a decade, from Werner Heisenberg's matrix mechanics in 1925 through Paul Dirac's relativistic extension in 1928, and it is among the most successful theoretical frameworks ever constructed. Its core elements are the wave function, the Schrödinger equation governing its time evolution, the Born rule connecting the wave function to measurement probabilities, and the projection postulate describing what happens to the wave function when a measurement is made. Every prediction this formalism generates, for every experiment ever performed at the quantum scale, has been confirmed. The formalism works without exception. The Schrödinger equation, published by Erwin Schrödinger in 1926, describes how the wave function of any quantum system evolves in time when no measurement is being made. It is a linear partial differential equation, and its linearity is the mathematical source of superposition. If psi1 and psi2 are both solutions to the Schrödinger equation, then any linear combination of them is also a solution. This means that if a particle can be in state 1 and can be in state 2, it can also be in a superposition of both. And this superposition will also evolve according to the Schrödinger equation, maintaining both components simultaneously. The Schrödinger equation is deterministic and continuous. Given the wave function at any moment, the equation determines the wave function at every subsequent moment, with no ambiguity. There is nothing in the Schrödinger equation that selects one outcome over another. There is nothing in it that corresponds to the collapse of the wave function to a definite value upon measurement. The projection postulate, which describes that collapse, was added to the formalism separately, as an additional rule outside the Schrödinger equation. It states that when a measurement of a quantum system is made and a specific outcome is obtained, the wave function instantaneously collapses to the eigenstate corresponding to that outcome. If an electron in a superposition of spin-up and spin-down is measured and found to be spin-up, the wave function collapses to the spin-up state. The spin-down component vanishes. Future measurements of the same spin axis will always give spin-up. The collapse is instantaneous, non-local in the sense that it affects the entire wave function simultaneously, regardless of how far it extends, and irreversible. The projection postulate is not derived from the Schrödinger equation. It is imposed on it as an additional physical rule that applies during measurements and only during measurements. This creates the measurement problem. The formalism contains two distinct and incompatible dynamical rules. One for when measurement is not happening and one for when it is, with no precise definition of what constitutes a measurement and no derivation of the second rule from the first. John von Neumann formalized this structure in his 1932 book Mathematical Foundations of Quantum Mechanics, which remains the definitive treatment of the formalism's logical structure. Von Neumann showed that the boundary between the quantum system being measured and the classical measuring apparatus can be placed at any point in the measurement chain without affecting the predicted outcome probabilities, but that the chain must terminate somewhere in a classical description if definite outcomes are to be produced. Where that termination occurs and why is left unspecified. The success of the formalism in predicting measurement outcomes has not required resolution of this interpretational problem. Physicists working in any experimental or applied field of quantum mechanics use the Born rule to calculate probabilities and the projection postulate to update the wave function after measurement without concern for what these rules mean at a fundamental level. The practice has a name, given to it by David Mermin of Cornell University in a 1989 paper in Physics Today, "Shut Up and Calculate." The phrase captures the pragmatic response of the majority of working physicists to the measurement problem. The formalism works, its predictions are confirmed, the interpretational questions are philosophy rather than physics, and the appropriate response is to use the formalism rather than interrogate its foundations. The difficulty with this response is not that it fails to produce correct predictions, it is that it does not constitute a scientific explanation of the phenomena. A complete physical theory should not merely predict what will be observed, it should describe what is happening. Quantum mechanics, as standardly formulated, describes the mathematical evolution of an abstract object to the wave function and provides a rule for extracting probabilities from it, without specifying what physical reality the wave function represents or why the rule takes the form it does. This is not a minor gap. It is the central conceptual problem of the most fundamental physical theory we have, and it has remained unresolved for nearly a century of effort by physicists whose technical credentials are beyond question. The formalism's internal tensions become visible when you press on the concept of measurement from a theoretical direction rather than an experimental one. What is a measurement in quantum mechanical terms? An interaction between a quantum system and something else. But everything is a quantum system. A measuring apparatus is a quantum system. The physicist operating the apparatus is a quantum system. If the Schrödinger equation applies universally, the interaction between the electron and the apparatus is simply the entanglement of one quantum system with another, evolving according to the Schrödinger equation, producing a superposition of correlated states of electron and apparatus. No collapse anywhere in this description. No definite outcome. The collapse appears only when the physicist is treated as standing outside the quantum mechanical description, as a classical observer whose observation produces a definite result by fiat. This is the von Neumann chain problem. Von Neumann showed in 1932 that the cut between quantum and classical, between the system described by the wave function and the observer who collapses it, can be placed at any point in the measurement chain without affecting the probabilities of outcomes. The cut can be between the electron and the apparatus. It can be between the apparatus and the physicist's eye. It can be between the physicist's eye and their brain. It can be between the brain's perceptual processing and the conscious experience of the physicist. Every choice of cut gives the same predictions. None of them is required by the mathematics. All of them are arbitrary. The formalism works regardless of where you put the cut, which means the formalism does not determine where the cut should be, which means the formalism is underdetermined with respect to its own interpretation. Eugene Wigner, one of the most accomplished theoretical physicists of the 20th century and a Nobel laureate, drew out the implications of this ambiguity in a thought experiment that became known as Wigner's friend. Wigner imagines a friend inside a sealed laboratory who measures an electron in a superposition of spin-up and spin-down. From the friend's perspective, the measurement produces a definite result. The wave function collapses and the friend records spin-up or spin-down. From Wigner's perspective outside the laboratory, applying the Schrödinger equation to the entire closed system of laboratory plus friend plus electron, the total wave function after the measurement is a superposition of friend observed spin-up and friend observed spin-down. Both descriptions are correct from within their respective frameworks. They are incompatible as descriptions of a single physical reality. Wigner's own response to this paradox was to suggest that consciousness was responsible for the collapse, that the observer's subjective experience was what selected a definite outcome. This is a position very few physicists have followed him to, but it illustrates how seriously the measurement problem was taken even by physicists of Wigner's stature. How the double slit became the most dangerous experiment in science. The double slit experiment becomes genuinely dangerous to intuition when one additional element is introduced, a detector that determines which slit each particle passes through. This modification, conceptually simple and experimentally achievable, produces a result that is as well confirmed as any result in physics and as difficult to absorb as anything in the history of science. Set up the double slit experiment with a detector at the slits capable of determining for each particle which slit it passed through. The detector does not need to block or deflect the particle. It only needs to obtain the which path information to create a physical record of which slit the particle used. Run the experiment and examine the pattern on the screen. The interference pattern is gone. In its place are two broad overlapping bands, one behind each slit, exactly what you would expect if each particle travelled through one slit or the other, as a classical particle would. The detector has destroyed the interference, not by physically blocking anything, not by changing the particle's trajectory, but by obtaining information about which path was taken. This result has been confirmed in every version of the experiment ever performed, with light, electrons, neutrons, atoms, and complex molecules. The interference pattern is present when which path information is unavailable, and absent when which path information is available, regardless of how the information is obtained or whether it is actually inspected by any human observer. The critical factor is not whether a physicist looks at the detector readout. It is whether the physical record of which path information exists anywhere in the universe. A detector that records which slit each particle uses but whose output is never read by anyone still destroys the interference pattern. A detector that is set up but switched off before any particle passes, so that no record is created, does not destroy it. The quantum eraser experiment, first proposed by Marlin Scully and Kai Druhl in 1982 and experimentally realized in multiple forms since then, makes this dependence on information existence even more precise. In a quantum eraser, which path information is created and then physically destroyed before the particle reaches the detector screen. When the which path information is erased, the interference pattern is restored. When it is retained, even in a form that is never consulted, the pattern is absent. The pattern on the screen depends not on what any observer knows, but on what physical record exists in the world. The delayed choice quantum eraser, realized experimentally by Yoon-Ho Kim and collaborators at the University of Maryland in 2000, extends this further. In their experiment, the decision about whether to erase the witch path information or retain it was made after the particle had already hit the detector screen. The particle, in this setup, produced a hit on the screen before it was determined whether it would contribute to an interference pattern or a non-interference pattern. Sorting the detected particles after the fact, by whether the witch path information for each one was erased or retained, reveals that the particles whose witch path information was erased do form an interference pattern, and those whose information was retained do not. The pattern present in the final data depended on a decision made after the particles had already been detected. The correct interpretation of this result is not that the future decision affects the past particle trajectory. It is that the correlations between the particle's final position and the later measurement are established by the quantum state of the entangled system from the start, and selecting subsets of particles based on the later measurement outcome reveals pre-existing correlations rather than retroactively altering anything. But this correct interpretation requires that the wave function of the entangled system maintains correlations across time and space in a way that has no classical analogue, and it does not reduce the conceptual difficulty of the original result. Whether witch path information exists or not determines the physical pattern that appears on the screen. Information about a particle's history is a physical variable that affects physical outcomes. This is not a figure of speech, it is a measured result. The double slit is dangerous because it does not permit a comfortable middle ground. You cannot believe that particles have definite trajectories through one slit or the other, and also explain the interference pattern. You cannot believe that the interference pattern results from some wave-like property of the particle, while also believing the particle is a point-like object localized in space. You cannot explain the disappearance of the interference pattern when witch path information exists without accepting that information itself, the physical existence of a record, has consequences for what patterns appear in the world. Every classical intuition you apply to this experiment produces a contradiction with the experimental result. The experiment is not a puzzle with a classical solution waiting to be found. It is a demonstration that classical intuitions are simply wrong at the quantum scale, and that whatever replaces them must be stranger than anything the pre-quantum history of physics produced. The measurement problem nobody has solved. The measurement problem is the name given to the set of difficulties that arise when quantum mechanics is taken seriously as a description of physical reality rather than as a calculation tool. It has several formulations, each exposing a different aspect of the same underlying tension. And despite nearly a century of effort by the most technically accomplished physicists of the 20th and 21st centuries, it remains genuinely unsolved. The simplest formulation is this: the Schrödinger equation is linear and deterministic. Applied to any quantum system, including the measuring apparatus, the particle being measured, and everything else in the universe, it predicts the evolution of the total wave function without collapse, without definite outcomes, and without any mechanism that selects one result over another. But measurements have definite outcomes. When you measure the spin of an electron, you get spin up or you get spin down. You do not get a superposition of both. The theory that describes the electron's state before measurement, applied consistently to the entire measurement interaction, does not by itself produce a definite outcome. Something additional must be invoked, the collapse postulate, and that postulate is not derived from the Schrödinger equation. It is imposed from outside. The deeper formulation, due to Schrödinger himself in 1935, is the cat paradox. Consider a box containing a cat, a radioactive atom, a detector, and a mechanism that breaks a vial of poison if the atom decays. The atom has a wave function that, after 1 hour, is a superposition of decayed and not decayed with equal probability. The Schrödinger equation, applied to the full system of atom, detector, mechanism, and cat, evolves the entire wave function into a superposition of two components. One in which the atom has decayed, the detector has fired, The poison has been released, and the cat is dead, and one in which none of this has happened and the cat is alive. The total wave function of the system is a superposition of a dead cat and a live cat. When the box is opened and the cat is observed, it is found to be in one definite state. But the Schrödinger equation applied without modification produces a superposition, not a definite outcome. Schrödinger's intent was satirical. He was demonstrating what he regarded as the absurdity of applying quantum superposition to macroscopic objects. The Copenhagen interpretation, the dominant framework of his era, would respond that the cat is a macroscopic object and that quantum superposition does not apply to macroscopic systems in the way it applies to atoms. But this response is not a derivation, it is an assumption. Nothing in the mathematics of quantum mechanics draws a line between microscopic and macroscopic systems. The Schrödinger equation applies to both, and if it applies to the atom, it applies, in principle, to the cat. The location of the boundary at which quantum behavior transitions to classical behavior, the Heisenberg cut, is not specified by the theory. It is inserted by assumption. The problem of why macroscopic objects appear classical when they are composed of quantum constituents is addressed by a phenomenon called decoherence, which is real, well understood, and important, but which does not, despite widespread claims to the contrary, solve the measurement problem. Decoherence describes the process by which the quantum coherence of a superposition state is suppressed through interaction with the surrounding environment. A large object like a cat interacts with enormous numbers of air molecules, photons, and other environmental constituents at every moment. Each interaction entangles the object with the environment, and the resulting entanglement disperses the phase relationships between the components of any superposition into the environment in a way that makes them practically impossible to recover or observe. The superposition is still present in the total wave function of the system plus environment, but its interference effects become immeasurably small on the macroscopic scale. The decoherence timescale for a dust particle of 1 microgram in air at room temperature is approximately 10 to the minus 31 seconds, a timescale so short that coherence is destroyed instantaneously for all practical purposes. For a cat, the timescale is unimaginably shorter still. This explains why we never observe macroscopic superpositions. The coherence that would make them observable is destroyed before any measurement could detect it. But it does not explain why one definite outcome is selected when a measurement is made. The total wave function of system plus environment after decoherence is a superposition of many components, each corresponding to a different measurement outcome, each decohered from the others so that they cannot interfere. All the components are still present. Decoherence explains why they cannot interfere with each other. It does not explain why only one of them is experienced as real. That question, the question of why there is a single definite outcome rather than a superposition of all outcomes, is the measurement problem, and decoherence does not answer it. Hugh Everett, and the interpretation nobody wanted. In 1954, a 24-year-old graduate student at Princeton named Hugh Everett III sat down to think about what quantum mechanics actually meant if you took its mathematics completely seriously. His advisor was John Wheeler, one of the most influential physicists of the 20th century. The question Everett set himself was disarmingly simple. What happens when the observer is included in the quantum mechanical description of a measurement? The answer he arrived at was so radical that it was rejected, ignored, and dismissed for decades before eventually becoming one of the most seriously debated interpretations of quantum mechanics in the field. Everett's central observation was that the measurement problem arises specifically because the observer is treated as standing outside the quantum mechanical description. The standard formalism applies the Schrödinger equation to the quantum system being measured and then invokes the collapse postulate from outside when the observer makes a measurement. But the observer is a physical system. The observer's brain and measuring apparatus are composed of atoms that obey quantum mechanics. There is no principled reason to place the observer outside the formalism. When the observer is included in the quantum mechanical description, along with the system being measured and the measuring apparatus, the Schrödinger equation predicts something specific. The total wave function of system plus apparatus plus observer evolves into a superposition of all possible measurement outcomes, each component of the superposition containing a version of the observer who has obtained a specific, definite result. In his 1957 doctoral thesis titled Relative State Formulation of Quantum Mechanics and published in Reviews of Modern Physics, Everett proposed that this superposition is real and complete. There is no collapse. There is no selection of a single outcome. When a measurement is made, the wave function of the universe branches into as many components as there are possible measurement outcomes, and each component contains an observer who has obtained the corresponding outcome and experienced it as the one definite result. Each branch is as real as every other. Each observer in each branch believes their outcome is the one that happened, because within their branch, it is. The different branches cannot communicate with or observe each other because they are decohered from each other. Their interference effects are suppressed by the same mechanism that makes macroscopic superpositions unobservable. To any observer within any branch, the world appears classical and definite, because that observer only has access to one branch. Everett called this the relative state formulation. The state of any subsystem is only defined relative to the state of the rest of the universe. An observer in a specific branch observes definite outcomes because those outcomes are the definite states of the system relative to the observer's branch. The ontological claim is that all branches exist. The epistemological claim is that any given observer can only be aware of one branch, the one they inhabit. So the appearance of a single definite outcome is a consequence of the observer's perspective, rather than evidence that only one outcome occurred. Wheeler arranged for Everett's thesis to be reviewed by Niels Bohr and his collaborators in Copenhagen, who were the dominant voices in the interpretation of quantum mechanics at the time. The Copenhagen group's response was dismissive. Bohr's close associate, Leon Rosenfeld, described the thesis as a hopeless confusion. The Copenhagen interpretation, as they understood it, required the classical world to be taken as a given, as the necessary starting point for any meaningful physical description. And Everett's attempt to derive the classical world from quantum mechanics was, in their view, misconceived from the start. Wheeler attempted to broker a meeting between Everett and the Copenhagen group to discuss the ideas directly. The meeting did not produce any change in positions. Everett left academic physics in 1956 before his thesis was published and spent his career working in operations research and defense consulting. He made enormous amounts of money applying mathematical optimization to logistics and weapons systems. He returned to quantum foundations only rarely. He died in 1982 at age 51, a heavy smoker and heavy drinker, having never seen his interpretation taken seriously by the mainstream physics community. His daughter Elizabeth, who had her own serious struggles, wrote in a suicide note that she was going to a parallel universe to be with her father. Whether Everett believed in the literal physical reality of the branches his mathematics described is a question his colleagues and biographers have debated, but the mathematics did not change after he left, and eventually the physics community returned to it. The revival began in earnest with Bryce DeWitt at the University of Texas at Austin, who independently recognized the power of Everett's approach and gave it the name by which it is now known, the many worlds interpretation. DeWitt published an accessible account of the interpretation in physics today in 1970 under the title Quantum Mechanics and Reality, which was the first exposure most physicists had to Everett's ideas. DeWitt was a distinguished relativist and one of the pioneers of quantum gravity, and his endorsement lent the interpretation a credibility it had not previously enjoyed. He and Neil Graham edited a collection of papers on the Everett interpretation published by Princeton University Press in 1973, which included Everett's original thesis, DeWitt's papers, and critical discussions, and which became a standard reference for physicists who took the foundations of quantum mechanics seriously. The interpretation gained further support from the development of quantum cosmology in the 1980s. Stephen Hawking, James Hartle, and others working on the quantum mechanics of the universe as a whole found that the Copenhagen interpretation was inapplicable to the cosmological context. Copenhagen requires a classical observer outside the quantum system being described, but there is no observer outside the universe. If quantum mechanics is to be applied to the universe as a whole, the observer must be inside the quantum system, which is precisely Everett's setup. Murray Gell-Mann at Caltech, who had won the Nobel Prize for his work on quark theory, and James Hartle at the University of California, Santa Barbara, developed a formalism called the consistent histories or decoherent histories interpretation through the late 1980s and 1990s, which provides a precise framework for assigning probabilities to histories of quantum systems without requiring an external observer. The consistent histories formalism is closely related to the Everett interpretation and can be regarded as a technical refinement of it, though its proponents have sometimes been reluctant to make that identification explicit. Why the Copenhagen response was never a real answer. The Copenhagen interpretation is not a single, well-defined position. It is a family of related views associated with Niels Bohr and his collaborators at the Institute for Theoretical Physics in Copenhagen in the 1920s and 1930s. And the various formulations of it that have been advocated since then differ from each other in important ways. What they share is the view that quantum mechanics is a theory about measurement outcomes rather than about physical reality, and that asking what is happening between measurements is either meaningless or outside the domain of physics. This position was enormously influential and allowed physicists to use quantum mechanics with confidence without needing to resolve the conceptual difficulties its formalism presents. It was also, from the perspective of philosophy of science, a sustained evasion of the central question. Bohr's version of the Copenhagen interpretation rested on the doctrine of complementarity. Quantum systems have mutually exclusive sets of classical properties such as wave-like and particle-like behavior, and any experimental arrangement that reveals one set necessarily precludes the other. The wave-particle duality is not a contradiction because no single experiment can reveal both aspects simultaneously. The classical concepts of wave and particle are both necessary for a complete description of quantum phenomena, but cannot be applied simultaneously. Bohr argued that the classical world of measuring instruments is a presupposition of any physical experiment, not something that needs to be derived from quantum mechanics. The quantum classical boundary is not a problem to be solved, but a feature of the structure of knowledge itself. This doctrine is philosophically interesting, but scientifically unsatisfying for a specific reason. It treats the classical world as given rather than explaining it. Bohr's position assumes that there is a classical realm of measuring instruments and observers that quantum mechanics does not need to account for, and it defines quantum mechanics as a theory of the interface between quantum systems and this pre-existing classical realm. But the classical world is composed of atoms that obey quantum mechanics. The assumption that macroscopic measuring instruments exist in definite classical states is not derivable from the quantum mechanical description of their constituents. Bohr's framework does not explain why the classical world exists. It assumes it. This is precisely what Everett tried to avoid. The most widely taught version of the Copenhagen interpretation in physics courses states that measurement collapses the wave function, that the collapsed state is the state of the system after measurement, and that questions about what the system was doing before the measurement are meaningless or unanswerable. This is operationally useful. It tells students how to calculate. It is not an interpretation of what is happening physically. It is a set of rules for extracting numbers from the formalism, supplemented by a prohibition on asking what those numbers describe. David Mermin's formulation of this as shut up and calculate was intended as criticism, not endorsement, though it has sometimes been adopted as a positive position. The Copenhagen interpretation also fails to specify what counts as a measurement. Bohr defined measurement in terms of interaction with a classical apparatus, but gave no criterion for when an apparatus is classical. Von Neumann showed that the quantum mechanical description can be consistently applied to any portion of the measurement chain, including the apparatus, and that the division between quantum and classical can be placed at any point without affecting the predicted outcome probabilities. This flexibility is not a feature. It is an admission that the theory contains an unresolved ambiguity at its core. The measurement process is both the mechanism by which definite outcomes are produced and the one process that the theory does not consistently describe. Several physicists who have thought carefully about this have concluded that the Copenhagen interpretation, while sufficient for practical calculations, is not a satisfactory physical theory in the same sense that general relativity or classical electrodynamics are satisfactory physical theories. John Bell, whose work on hidden variables and entanglement is among the most important contributions to quantum foundations of the 20th century, was particularly direct. In a 1990 paper titled Against Measurement, published in the journal Physics World, Bell listed the concepts he found unacceptably vague in the standard formalism. The terms system, apparatus, measurement, and observer are all used without precise definition, and the theory's predictions depend on distinctions among these terms that the theory itself does not provide. Bell's own view was that quantum mechanics as standardly formulated was incomplete, and that a more precise theory would either add variables, specify when collapse occurs, or abandon collapse entirely. Everett's interpretation belongs to the third category. Decoherence and why the world looks classical when it is not. Decoherence is one of the most significant theoretical developments in quantum physics of the last 50 years. It explains, in rigorous and experimentally confirmed terms, why the macroscopic world appears classical even though it is composed of quantum constituents. It does not solve the measurement problem, but it dissolves one of the most commonly raised objections to taking the Schrödinger equation literally, the objection that we never observe superpositions of macroscopic objects. Understanding why decoherence does and does not resolve the measurement problem is essential to understanding what Everett's interpretation actually claims and why it is taken seriously. The central concept is quantum entanglement. When two quantum systems interact, they generally become entangled. The wave function of the combined system cannot be written as a product of separate wave functions for each system individually. The state of each system is correlated with the state of the other, and these correlations are non-classical in the specific sense established by Bell's theorem and the aspect experiments. Once two systems are entangled, measurements performed on one are correlated with measurements performed on the other in ways that cannot be explained by any shared classical property they possessed before the interaction. Decoherence is what happens when a quantum system becomes entangled with an environment containing an enormous number of degrees of freedom. A macroscopic object in any ordinary environment is constantly bombarded by air molecules, photons from ambient light and thermal radiation, and interactions with its supporting surface. Each collision or photon absorption entangles the object with the environment. The object's quantum state becomes entangled with the states of every particle it has interacted with, and those particles interact with others, spreading the entanglement through the environment in a branching cascade. The initially local quantum coherence of the object's state is dispersed into correlations that extend throughout the environment and are impossible to recover by any local measurement. The practical consequence is that interference between different components of the object's superposition becomes immeasurably small. The interference terms in the density matrix, the quantum mechanical object that describes the statistical state of a system entangled with an environment, decay on timescales that depend on the mass of the object, the temperature and density of its environment, and the spatial separation of the components of the superposition. For a grain of dust of mass 10 to the minus 12 grams at room temperature in air, the coherence time is approximately 10 to the minus 31 seconds. For a cat, the relevant number is many orders of magnitude smaller still. In practice, quantum coherence on macroscopic scales is destroyed instantaneously and irreversibly. This is why we do not observe superpositions of macroscopic objects. The superpositions exist in the sense that the total wave function of system plus environment contains components corresponding to all classical states. But the interference between those components is suppressed to the point where no measurement restricted to the system alone can detect it. The reduced density matrix of the system, obtained by tracing over the environmental degrees of freedom, is diagonal in the basis of classical states. It looks like a classical probability distribution over the possible states rather than a quantum superposition of them. This is what Wojciech Zurek at the Los Alamos National Laboratory, who developed the modern theory of decoherence through the 1980s and 1990s, has called the emergence of classicality from quantum mechanics. Zurek's work, along with contributions from H. Dieter Zeh at Heidelberg, who first appreciated the importance of environmental entanglement in 1970, and from Juan Pablo Paz and others, has given decoherence a precise quantitative framework that has been experimentally confirmed in systems carefully engineered to test it. Serge Haroche and collaborators at the École Normale Supérieure in Paris conducted experiments through the 1990s and 2000s in which microwave photons were trapped in a high-quality cavity, and their decoherence was monitored in real time as they interacted with the cavity walls. The decoherence of superposition states followed the theoretical predictions quantitatively across a range of conditions. Haroche received the Nobel Prize in Physics in 2012, shared with David Wineland, for this work. What decoherence does not explain is why any single observer experiences a single definite outcome rather than a superposition. After decoherence, the total wave function of system plus environment is a superposition of many components, each corresponding to a definite classical outcome, each entangled with a specific environmental state, each decohered from all the others. Decoherence explains why the components cannot interfere. It does not explain why there is one component from the observer's perspective rather than all of them. This is the remaining core of the measurement problem, and it is exactly the question that Everett's interpretation answers by denying its premise. There is not one component from the observer's perspective. There are as many components as there are outcomes, and each component contains an observer who experiences that outcome as the single, definite result. The question of why a single outcome is experienced is replaced by the question of why any given observer finds themselves in one branch rather than another, which in the many worlds framework has the answer. They find themselves in all branches simultaneously as different versions of themselves. The many worlds interpretation taken completely seriously. The many worlds interpretation, the name given by Bryce DeWitt in the late 1960s to Everett's relative state formulation, is not a modification of quantum mechanics. It is quantum mechanics, taken without any additional postulates beyond the Schrödinger equation and the Born rule as a derived consequence, rather than a primitive assumption. Its claim is that the wave function is real, that the Schrödinger equation governs its evolution without exception, and that every branch of the wave function that quantum mechanics predicts corresponds to a real physical world. The other worlds are not theoretical conveniences or mathematical fictions. In the many worlds interpretation, they are as physically real as the world we observe. The consequence of taking this seriously as a physical claim is that every quantum event with multiple possible outcomes produces a branching of the universe into multiple copies, each containing a version of every object and observer in the universe. When a physicist measures the spin of an electron in a superposition of up and down, the universe branches. One version of the physicist obtains spin up, another obtains spin down. Both are real. Both proceed as separate, non-interacting histories. The electron does not collapse to one definite spin. Both spins exist, each in its own branch. The information about which branch any observer is in is encoded in the observer's physical state, in the specific pattern of neural activity and memory records that constitutes the observer's experience of having obtained a definite measurement result. The branching happens continuously and at every scale. Every interaction between quantum systems that entangles them produces branching, not just laboratory measurements of exotic quantum properties. The decoherence that occurs between a gas molecule and a dust particle, between a photon and a retinal cell, between a cosmic ray and an atmospheric atom, all produce branchings that expand the multiverse in every instant. The number of branches is not fixed or countable in any finite sense. It grows without bound as the universe evolves, producing a structure of branching histories that is, in the many worlds interpretation, the complete description of physical reality. The branches do not communicate with each other once they have formed. This is a direct consequence of decoherence. The interference terms between different branches are suppressed by the decoherence of their environmental entanglement to values so small that no measurement could detect them. Different branches are effectively separate worlds, each evolving according to the Schrödinger equation, each internally consistent, each containing observers who have no access to information from any other branch. The many worlds interpretation makes the observable universe we experience a single branch of an enormously larger reality, and the absence of any observable evidence for the other branches is explained by the decoherence that separates them. The question of what counts as a branch is not trivially answered. The wave function does not have natural joints at which it divides into discrete separate worlds. The branching is continuous and gradual, occurring as decoherence progressively suppresses interference between components of the total wave function. David Deutsch at Oxford, who has been one of the most persistent and technically rigorous defenders of the many worlds interpretation since the 1980s, argues that the branches are defined operationally. A branch is a region of the wave function that is decohered sufficiently from all other regions that no measurement accessible to an observer within it could detect the interference terms. This is an approximate definition, and it depends on the practical limits of measurement technology rather than on any fundamental feature of the wave function itself. Simon Saunders at Oxford, David Wallace at the University of Southern California, and others working in the Everettian program have developed more formal treatments of branch structure using the concept of decoherence-defined quasi-classical histories. But the fundamental fuzziness of where one branch ends and another begins remains a feature of the interpretation that its critics regard as problematic. What branches are and why you cannot return to them. The branches of the many worlds wave function are not alternate universes in the sense of science fiction, separate spacetimes with different laws of physics, different histories from the beginning of time, or different fundamental constants. They are components of the same wave function, evolving within the same spacetime according to the same physical laws, differentiated only by the specific outcomes of quantum events that have occurred within them. The branch in which a physicist measured spin-up and the branch in which the same physicist measured spin-down share the same physical laws, the same prior history up to the moment of measurement, and the same future prospects constrained by those laws. They differ only in which measurement outcome the physicist recorded. The irreversibility of branching follows from decoherence. Once two components of the wave function have become entangled with environments that differ in their states by vast numbers of degrees of freedom, the interference between them is suppressed to immeasurably small values and cannot be restored by any operation accessible to an observer within either branch. To restore interference between two branches would require assembling the complete quantum states of all the environmental particles that have interacted with the system since the branching occurred, reversing every one of those interactions precisely and coherently recombining the components. For any macroscopic system in any ordinary environment, the number of environmental particles involved after even a microsecond is of order 10 to the 23rd or more, and the precision required to reverse all their interactions is so extraordinary that it is effectively impossible within any timescale relevant to physics. This irreversibility has a direct thermodynamic connection. The second law of thermodynamics, the principle that entropy in a closed system does not decrease, is in the many worlds interpretation a consequence of the branching structure of the wave function and the practical impossibility of reversing decoherence. Entropy increases because information about the quantum state of a system is progressively dispersed into correlations with the environment through the branching process, and recovering that information would require an operation whose complexity grows exponentially with time. The arrow of time, the fact that physical processes proceed from lower entropy states to higher entropy states and not in reverse, is in this picture a reflection of the direction of branching. Earlier branches are accessible in memory. Later branches are not yet determined. The practical impossibility of recombining branches does not mean that quantum interference between macroscopic superpositions is theoretically forbidden. In principle, if you could reverse all the environmental entanglement precisely enough, you could restore the coherence of a macroscopic superposition and observe the interference. The many worlds interpretation does not forbid this. It only says that the operation required to do it is extraordinarily complex, so complex as to be practically impossible in any natural setting. This is a distinction that matters for the question of experimental tests of the interpretation. If branches are truly separate with no possibility of interference, the many worlds interpretation makes no predictions different from Copenhagen, and the two are empirically indistinguishable. If in sufficiently controlled quantum systems, interference between branches can be maintained and observed, this is consistent with many worlds but is also predicted by Copenhagen, which simply says the wave function has not collapsed yet. The interpretations agree on all experimental predictions precisely because the many worlds interpretation contains no additional physics beyond the Schrödinger equation, and Copenhagen contains no physics that differs from the Schrödinger equation in any regime where collapse cannot be directly observed. What branches are, therefore, is real physical histories, defined by the specific quantum measurement outcomes that have occurred within them, separated from all other branches by decoherence that makes their interference effects immeasurably small, and their recombination practically impossible, containing within them all the observers and physical structures that exist in the post-branching world, and entirely undetectable from any other branch by any measurement accessible to an observer within either. They are, in every observable sense, separate worlds. They are, in the mathematical sense of the wave function, components of a single, total quantum state. The Born rule problem and why many worlds is not yet complete. The most serious technical objection to the many worlds interpretation is not philosophical, it is mathematical, and it concerns the Born rule, the central rule of quantum mechanics that connects the wave function to the probabilities of measurement outcomes. In the standard formulation of quantum mechanics, the Born rule is a postulate. It is asserted as a fundamental rule alongside the Schrödinger equation, without derivation from anything more basic. In the many worlds interpretation, the Born rule cannot be a primitive postulate because the interpretation's central claim is that the Schrödinger equation is the only fundamental rule of quantum dynamics, with no additional postulates beyond the reality of the wave function. If the many worlds interpretation is to be a complete theory, it must derive the Born rule from the structure of the wave function and the Schrödinger equation alone. This derivation has not been fully achieved, and the gap it represents is the most significant unresolved problem in the Everettian program. The difficulty can be stated precisely. In the many worlds interpretation, when a quantum system in a superposition of states is measured, the universe branches into multiple components, each containing a version of the observer who has obtained a specific outcome. All branches are real. All branches contain real observers. The Born rule says that the probability of any observer finding themselves in the branch corresponding to a particular outcome is equal to the squared magnitude of the wave function component corresponding to that outcome. For a spin measurement on an electron in a superposition of spin-up with amplitude 1 over root 2 and spin down with amplitude 1 over root 2, the Born rule assigns equal probability of 50% to each outcome. In the many worlds interpretation, both outcomes occur and both branches exist. What does it mean to say there is a 50% probability of being in the spin-up branch when you will definitely be in both? The concept of probability, as it is usually understood, as the likelihood of one outcome among mutually exclusive alternatives, does not obviously apply when all outcomes occur. This is sometimes called the incoherence problem. The very concept of probability seems incoherent in a framework where every outcome is certain to occur in some branch. It is also called the quantitative problem. Even setting aside the incoherence issue, why should the probabilities be given by the squared magnitudes of the wave function components, rather than, say, by the number of branches corresponding to each outcome? If a superposition has two branches, why does an observer not have a 50% chance of finding themselves in each branch regardless of the relative amplitudes, rather than a probability proportional to the amplitude squared? The most developed attempt to derive the Born rule within the many worlds framework uses a decision theoretic argument developed by David Deutsch in a 1999 paper published in the Proceedings of the Royal Society, and subsequently refined by David Wallace in a series of papers culminating in his 2012 book, The Emergent Multiverse. The argument does not try to derive the Born rule from counting branches. Instead, it treats the question of how a rational agent should bet on the outcomes of quantum measurements, given that the many worlds interpretation is correct and all outcomes occur. Deutsch and Wallace argue that any rational agent who accepts the many worlds interpretation and who satisfies certain axioms of rationality is committed to betting on quantum outcomes using probabilities equal to the Born rule weights. The argument is not that the Born rule is empirically derived from observed frequencies. It is that a rational agent who understood quantum mechanics would act as if the Born rule were correct, because any other betting strategy would be irrational given the structure of the branching wave function. The decision theoretic derivation has been criticized on multiple grounds. Adrian Kent at Cambridge has argued that the rationality axioms Deutsch and Wallace impose beg the question. They assume, in effect, that branches with larger amplitude should be weighted more heavily, which is what the Born rule says, rather than something independent of it. Other critics argue that the decision theoretic framework applies only to agents making bets before branching occurs, and that the notion of probability for a post-branching observer, who will definitely experience a specific outcome, cannot be recovered from any analysis of pre-branching rational betting. The debate continues in technical publications, with Wallace and his collaborators responding to each objection and critics identifying what they regard as remaining gaps. An alternative approach uses the concept of branch counting in the limit of many measurements. If an observer performs a large number of measurements of identically prepared quantum systems, the many worlds wave function develops branches corresponding to all possible sequences of outcomes. The branches in which the observed frequencies of outcomes match the Born rule predictions have, in the Schrödinger wave function, a total squared amplitude that approaches 1 as the number of measurements grows large, while the branches in which the observed frequencies deviate significantly from the Born rule predictions have total squared amplitude approaching 0. This is a form of the law of large numbers for quantum mechanics, and it establishes that in the many worlds framework, A born rule violating observer is one who finds themselves in a branch of vanishingly small amplitude. Whether this constitutes a derivation of the born rule or merely a restatement of it in many worlds language is disputed. The problem is not fully solved, and the many worlds interpretation remains, in this specific sense, incomplete. The problem connects to a broader question about the meaning of probability in physics. In classical statistical mechanics, probability represents ignorance about the exact microstate of a system. In standard quantum mechanics, the born rule probability represents a fundamental indeterminacy, not merely ignorance. In the many worlds interpretation, neither of these characterizations fully applies. There is no ignorance, because all branches are real and their contents are determined by the wave function. There is no indeterminacy, because all outcomes occur. The probability is, in some sense, a measure of how much of the total wave function is associated with any given outcome, which is why it equals the squared amplitude. But translating this measure-theoretic notion into a statement about what any particular observer should expect to experience requires bridging the gap between the objective structure of the wave function and the subjective perspective of an observer in one branch. And that gap is precisely what the born rule problem concerns. Jeffrey Bubb at the University of Maryland and Itamar Pitowski developed an alternative approach to the born rule in the early 2000s, arguing that the rule can be derived from operational constraints on how any rational agent in a quantum world must assign probabilities, without invoking the many-world structure directly. Their argument uses a quantum analogue of the Dutch book argument from classical probability theory. An agent whose probability assignments do not follow the born rule is committed to accepting bets that guarantee a loss regardless of outcomes. This operationalist derivation is different from the decision-theoretic approach of Deutsch and Wallace, and it has attracted both support and criticism. Its critics argue that operationalist approaches smuggle in classical probability reasoning at points where quantum reasoning should be applied. Its proponents argue that the born rule's universality follows naturally from the operational structure of quantum measurement, without requiring any specific interpretation of the wave function. What all of these approaches share is the recognition that the born rule cannot be treated as a primitive postulate in a theory that takes the wave function as the complete description of reality. Something must justify it, whether from rationality constraints, from the structure of the wave function itself, or from the operational practice of quantum measurement. The specific justification chosen has implications for what kind of theory the many worlds interpretation is, whether it is a complete fundamental theory, a practical framework for calculating, or a metaphysical picture whose connection to measurable predictions requires additional assumptions. This is not a peripheral question about the interpretation's fine details. It is a question about whether the interpretation is finished or whether it remains a program awaiting completion. Quantum suicide and what it would actually prove. The many worlds interpretation makes one prediction that no other interpretation of quantum mechanics shares. It implies that an observer who performs a sufficiently extreme experiment will survive, from their own perspective, with certainty, even if the probability of survival in any given branch is arbitrarily small. This prediction is the basis of the quantum suicide thought experiment, and the fact that it is a genuine logical consequence of the interpretation, rather than a rhetorical flourish, reveals something important about what the many worlds interpretation is actually committed to. The quantum suicide experiment was independently proposed by Hans Moravec in 1987 and by Max Tegmark at the Massachusetts Institute of Technology in a 1998 paper that formalized it precisely. The setup is as follows. An observer sits in front of a device that measures the spin of an electron in a superposition of spin up and spin down. If the electron is measured as spin up, a harmless signal is produced and the observer survives. If it is measured as spin down, the device immediately kills the observer before any conscious experience of the outcome is possible. The experiment is repeated every second. In the Copenhagen interpretation, each run of the experiment gives a 50% chance of survival, and the probability of surviving 100 consecutive runs is 1/2 to the 100th power, approximately 10 to the -30, which is essentially 0. The observer should expect with near certainty to be dead after 100 runs. In the many worlds interpretation, the analysis is different. After each run of the experiment, the universe branches. One branch contains a live observer who recorded spin-up, and one branch contains a dead observer for whom the experiment ended with spin-down. In the branches where the observer is alive, the experiment continues. In the branches where the observer is dead, it does not. After 100 runs, the vast majority of branches contain a dead observer who survived only a small number of runs. But there is a branch with an extremely small wave function amplitude in which the observer has recorded spin-up 100 times in succession and is still alive. In the many worlds interpretation, this branch is real. The observer in this branch has survived. The implication is that any observer who performs this experiment from their own first-person perspective will experience an unbroken sequence of survival. At each step, they will find themselves in the branch where they survived, because they cannot find themselves in a branch where they are dead. Their subjective experience is necessarily continuous. Every version of themselves that has any further experience is a surviving version. After 100 runs, the probability of survival from any external observer's perspective is essentially 0. But the surviving observer in the tiny amplitude branch experiences having survived all 100 runs and cannot distinguish their situation from one in which the Copenhagen interpretation is correct, and they got very lucky. Tegmark's formalization of this thought experiment was not an endorsement of attempting it. It was a demonstration that the many worlds interpretation makes a qualitatively different prediction from Copenhagen regarding the first-person experience of an observer in this situation. If Copenhagen is correct, the observer should expect death with near certainty. If many worlds is correct, the observer should expect from their own perspective to survive indefinitely. The experiment is not one anyone could responsibly perform, and even if someone did, the surviving observer's testimony would not constitute scientific evidence. The surviving observer would expect to be alive regardless of which interpretation is correct if Copenhagen gives them even a small chance of survival per run, and an extraordinarily improbable Copenhagen survival is not distinguishable from a many-world survival by the survivor alone. The quantum immortality extension goes further. If the many worlds interpretation is correct and consciousness cannot experience its own termination, then any observer should expect, from their own first-person perspective, to survive indefinitely regardless of what happens to other versions of themselves in other branches. This is not a prediction that can be tested or that the many worlds interpretation straightforwardly implies, because it requires assumptions about consciousness and personal identity across branches that go beyond the physics. But the quantum suicide argument does follow from the many worlds physics without those additional assumptions, and it illustrates the kind of radical departure from ordinary intuition that taking the interpretation literally requires. The branches in which the observer is dead are real, physical, and contain real observers who are simply not the ones having further experiences. The continuity of experience is not a feature of reality in the many worlds interpretation. It is a feature of the perspective of any particular observer thread, the physicists who believe it, and why their reasons are not mystical. The many worlds interpretation is not a minority view held by physicists attracted to mysticism or science fiction. Among the physicists who have worked most carefully on the foundations of quantum mechanics, it commands significant and growing support, and the reasons they give for finding it compelling are technical and precise, rather than romantic. Understanding those reasons requires distinguishing between the many worlds interpretation as a physical claim and as a metaphysical preference, and recognizing that the physicists who endorse it do so primarily because they find the alternatives less satisfactory as accounts of physical reality. David Deutsch at the University of Oxford is the most prominent living advocate of the many worlds interpretation, and his case for it is rooted in the parallel processing argument from quantum computing, rather than in any foundational preference for many-world ontologies. Deutsch argues that quantum computers perform computations that are physically carried out across a vast number of parallel computational processes simultaneously. When a quantum computer factors a large number using Shor's algorithm, the computation requires an exponential number of arithmetic operations that no single processor could perform in the available time. In the many worlds interpretation, these operations are performed in parallel across a correspondingly large number of branches of the wave function, each branch carrying out a portion of the computation. The computational power of quantum computers is, in this account, evidence for the physical reality of the other branches, because without them, there would be no place for the computation to be performed. This argument does not logically compel the many worlds interpretation. Copenhagen would say the computation is performed by the wave function's quantum parallelism without any branches being real. But Deutsch regards Copenhagen's refusal to say where the computation happens as explanatorily bankrupt. Sean Carroll at Johns Hopkins University, who shifted his public position on the many worlds interpretation towards strong endorsement over the past decade and articulated it in his 2019 book, Something Deeply Hidden, makes a different argument grounded in theoretical parsimony. Carroll's case is that the many worlds interpretation is the simplest interpretation of quantum mechanics in the sense that it requires the fewest additional postulates beyond the wave function and the Schrödinger equation. Every other interpretation adds something to the formalism. The Copenhagen interpretation adds the collapse postulate and the classical quantum boundary, neither of which is derived from the Schrödinger equation. The pilot wave interpretation of Louis de Broglie and David Bohm adds hidden variables and a non-local quantum potential. The objective collapse models of Girardi, Rimini, and Weber add spontaneous localization terms to the Schrödinger equation. Each addition is an unexplained supplementary structure. The many worlds interpretation adds nothing. It takes the Schrödinger equation and the wave function and accepts everything they predict without modification. Max Tegmark at MIT, beyond his contribution to the quantum suicide argument, has been a consistent public advocate for the many worlds interpretation and has embedded it within his broader framework of the mathematical multiverse. Tegmark's argument is that the multiple interpretations of quantum mechanics are unified by the recognition that all are committed to a level of parallel reality. Copenhagen requires a classical world that cannot be derived from quantum mechanics. Pilot wave theory requires all wave function branches to exist as real guiding structures, even though only one is occupied. Only many worlds is fully consistent in treating the wave function as the complete physical description of reality without additional unobservable structure. Simon Saunders, Jonathan Barrett, Adrian Kent, and David Wallace at Oxford organised a major conference on the Everett interpretation in 2007 to mark the 50th anniversary of Everett's thesis, bringing together the leading researchers in quantum foundations with expertise in both physics and philosophy of physics. The resulting volume, Many Worlds, Everett, Quantum Theory and Reality, published by Oxford University Press in 2010, provides the most technically rigorous collective assessment of the interpretation available. The contributors include both advocates and critics, and the arguments are conducted at a level of precision that distinguishes them clearly from the popular discussions the topic often generates. The conclusion of the volume is not consensus, but a sharply defined set of open problems and a clear articulation of what would be required to resolve them. Survey data on physicist attitudes toward interpretations of quantum mechanics suggest that the many worlds interpretation has moved from a fringe position to a substantial minority view over the past 3 decades. A survey conducted by Max Tegmark at the 1997 UMBC Quantum Mechanics Conference found approximately 17% of respondents favouring Everett's interpretation. A 2013 survey by David Schlosshauer and collaborators, published in Studies in History and Philosophy of Modern Physics, found the many worlds interpretation among the top 3 positions, with roughly 18% support among a sample of quantum physicists. Informal surveys at recent Quantum Foundations meetings have reported higher numbers, with some finding many worlds as the plurality position among specialists in quantum foundations specifically. The trend toward increased acceptance reflects the technical developments in decoherence theory and the decision-theoretic derivation of the Born rule that have made the interpretation more precisely formulated and its remaining problems more clearly identified. The experiments that cannot distinguish between interpretations. One of the most significant features of the debate between quantum interpretations is that all of them, by construction, make identical empirical predictions for every experiment that has ever been performed or that current technology can perform. This is not an accident. Every interpretation of quantum mechanics is designed to reproduce the predictions of the standard formalism, which has been confirmed without exception. The interpretations differ in what they say is happening, not in what they predict will be observed. This makes the question of which interpretation is correct, in a narrow empirical sense, currently undecidable by experiment, and raises the question of whether the choice between interpretations is a scientific question at all. The Copenhagen interpretation, the many worlds interpretation, the pilot wave interpretation, and the objective collapse models all predict the same outcomes for every measurement of the spin, position, momentum, energy, or any other observable property of any quantum system. They differ in what they say the wave function represents, in whether the collapse of the wave function is a real physical process or a mathematical convenience, in whether there are hidden variables underlying the probabilities, and in whether other branches of the wave function are physically real. But for any experiment that can be run in a laboratory, they agree on every number. This agreement is guaranteed by the fact that they all reproduce the predictions of the Schrödinger equation combined with the Born rule, and those predictions are what determine measurable outcomes. There is one class of experiments that could in principle distinguish between interpretations that posit real collapse and interpretations that do not. Experiments that achieve quantum coherence on scales large enough that the difference between a collapsed wave function and an uncollapsed one would produce different interference effects. The objective collapse models of Ghirardi, Rimini, and Weber, published in Physical Review D in 1986, add a specific modification to the Schrödinger equation that introduces spontaneous localization events at a rate that is negligibly small for individual particles, but grows rapidly with the number of particles in a system. For a single electron, the spontaneous localization rate is approximately 10 to the minus 16 per second, so slow as to be undetectable. For a macroscopic object containing 10 to the 23rd particles, the rate is effectively instantaneous, ensuring that macroscopic superpositions collapse on timescales far shorter than any measurement. The GRW model and its successors, including the continuous spontaneous localization model of Philip Pearl and the Diossi-Penrose model that connects collapse to gravitational effects, make predictions that differ from the no-collapse models by amounts that depend on the mass and size of the superposed system. Current experiments with nanoparticles, molecular clusters, and mechanical oscillators are approaching the mass scales at which objective collapse models predict measurable deviations from the no-collapse Schrödinger evolution. The macro experiment, proposed for a space-based platform to avoid thermal noise, aims to demonstrate spatial interference of nanoparticles with masses of order 10 to the minus 17 kilograms, which is within the range where the Diossi-Penrose model predicts suppression of coherence beyond what decoherence alone would produce. Markus Arndt's group at the University of Vienna has performed matter wave interference experiments with increasingly massive molecules, reaching carbon fullerene clusters of several hundred atoms, and demonstrating coherence at distances and masses that would have been thought impossible when quantum mechanics was first developed. The experimental trajectory points towards a regime where objective collapse models either produce measurable deviations from standard quantum mechanics or are experimentally ruled out at those mass scales. The many worlds interpretation, by contrast, predicts exactly the same interference pattern as standard quantum mechanics at any mass scale because it adds nothing to the Schrödinger equation. If objective collapse models are experimentally ruled out at large mass scales, many worlds gains no direct confirmation. It was already predicting what standard quantum mechanics predicts. What is gained is the elimination of a class of alternatives that add collapse to the formalism. The surviving interpretations after such experiments would be those that do not modify the Schrödinger equation. Many worlds, pilot wave theory, and the various no-collapse versions of Copenhagen. Distinguishing among these remaining interpretations is harder still, because they agree even more completely on experimental predictions, differing only in their metaphysical commitments about what the wave function represents. The pilot wave interpretation, developed by Louis de Broglie in the late 1920s and independently revived and completed by David Bohm in 1952, provides an alternative to both Copenhagen and many worlds that restores the classical picture of particles with definite positions at all times. In the pilot wave interpretation, particles are real point-like objects that move under the guidance of the wave function, which acts as a physically real guiding field. The wave function does not collapse. It continues to evolve according to the Schrödinger equation. But only one branch of the wave function, the one containing the actual particle, produces observable effects. The other branches of the wave function are real in the sense that they contribute to the guiding field, but they are empty. No particle inhabits them. This gives pilot wave theory a kind of many-world structure, with a real wave function that includes all branches, but a single actual particle trajectory that threads through only one branch. Bell, who developed great respect for the pilot wave interpretation, described it as the best-kept secret in physics, noting that it demonstrated unambiguously that quantum mechanics can be given a deterministic ontology without any appeal to observers or measurements. The pilot wave interpretation is fully deterministic. Given the initial positions of all particles and the initial wave function, the subsequent evolution is determined exactly by the guidance equation. The apparent randomness of quantum mechanics arises from ignorance about the exact initial particle positions, distributed according to the Born rule. This is similar in structure to classical statistical mechanics, where apparent randomness reflects ignorance about exact microstates. Bohm showed that if the initial particle positions are distributed according to the squared wave function amplitude, as the Born rule requires, they remain so distributed at all subsequent times. The Born rule distribution is an equilibrium distribution of the pilot wave dynamics. The pilot wave interpretation's difficulties are different from many worlds' difficulties rather than smaller. It is explicitly non-local. The guidance equation makes the velocity of each particle depend on the positions of all other particles simultaneously, regardless of their separation. This non-locality is required by Bell's theorem. Any hidden variable theory that reproduces the correlations of entangled quantum systems must be non-local. In the pilot wave interpretation, the non-locality is explicit and exact. The wave function is a field on configuration space, not on physical three-dimensional space, and a change in one particle's position instantaneously affects the guiding field experienced by every other particle. Making the pilot wave interpretation consistent with special relativity, which prohibits superluminal signaling, requires that the non-local influences not be usable for communication, which Bohm's guidance equation ensures. But the fundamental non-locality remains in tension with relativistic space-time structure in a way that has not been fully resolved. What quantum computing implies about the reality of other branches. Quantum computing is the most practically significant application of quantum mechanics developed since the laser, and it is also, in Deutsch's analysis, the most compelling evidence available for the reality of the other branches of the many worlds wave function. The argument is not that quantum computers proved the many worlds interpretation. It is that the computational power of quantum computers is most naturally explained by the physical reality of parallel processing across branches, and that any alternative account requires either a denial of the demand for physical explanation or an alternative account of where the computation is happening that is at least as ontologically committed. A classical computer processes information by manipulating bits, each of which is at any moment in one of two definite states, 0 or 1. The number of operations a classical computer can perform per unit time is proportional to the number of bits and the clock speed, both of which are subject to physical limits. A quantum computer processes information using quantum bits, qubits, each of which can be in a superposition of 0 and 1 simultaneously. The computational power of a quantum computer arises not from any single qubit being in two states at once, but from the entanglement among many qubits, which creates a wave function that is a superposition of an exponential number of classical bit strings simultaneously. A register of 300 qubits has a wave function that is a superposition of 2 to the 300th power, approximately 10 to the 90th, distinct classical states. This number exceeds the total number of atoms in the observable universe. Quantum algorithms exploit this superposition through carefully designed sequences of quantum gates that manipulate the wave function so that the interference between different components amplifies the components corresponding to the correct answer and suppresses those corresponding to incorrect answers. Peter Shor's algorithm, published in 1994, factors large integers in polynomial time, exponentially faster than the best-known classical algorithm. Lovegrover's algorithm, published in 1996, searches an unsorted database of n items in time, proportional to the square root of n, rather than the n steps required classically. Both algorithms require the quantum computer to exploit the interference between exponentially many superposition components simultaneously. Deutsch's question is, where does the computation happen? A quantum computer factoring a 2000-digit number using Shor's algorithm performs an exponential number of arithmetic operations. These operations are performed physically, in the sense that physical systems undergo physical changes that implement them. In the many worlds interpretation, they are performed in parallel across an exponential number of branches of the wave function, each branch performing a portion of the computation. The branches then interfere to produce the correct answer as a measurement outcome. The physical story is complete and consistent. A real physical process happens in real branches, and the result is extracted by measuring the quantum register. In the Copenhagen interpretation, the computation is performed by the wave function's quantum superposition. But the wave function is not a description of physical reality. It is a catalogue of probabilities for measurement outcome. The computation somehow produces the correct answer without any physical story of where the intermediate steps occur. Deutsch regards this as unsatisfactory. He is not asking Copenhagen to identify a mechanism in the ordinary sense. He is noting that the computation requires physical resources, in the sense that it requires more arithmetic operations than any single classical process could perform, and that Copenhagen offers no account of what physical resources are being used. The many worlds interpretation provides an account. Whether that account is required, or whether physics has any obligation to provide such an account for every computational process, is a question on which physicists and philosophers of physics have disagreed sharply. The practical progress in building quantum computers has accelerated substantially in the past decade. Google's Sycamore processor, a 53-qubit superconducting chip, demonstrated in 2019 a computation that Google's team estimated would take the most powerful classical supercomputer approximately 10,000 years, while Sycamore completed it in 200 seconds. The calculation, sampling from a specific random circuit distribution, is not a practically useful algorithm, but the demonstrated speedup is consistent with quantum parallel processing across an enormous number of branches. IBM's quantum computing program has produced processors with over 400 qubits as of 2023, and error-corrected logical qubits capable of running algorithms at the scale required for Shor's algorithm are a near-term target. As quantum computers grow in power and the speed-ups they demonstrate become more dramatic, the question of where the computation is physically happening becomes more pressing rather than less. The cosmological version, the wave function of the universe. The many-worlds interpretation is not merely an interpretation of laboratory quantum mechanics. It is a framework for quantum cosmology, the application of quantum mechanics to the universe as a whole. In this context, the interpretation is not one option among several with equal standing. It is arguably the only fully consistent framework available, because the alternatives that rely on external observers or classical apparatuses cannot be applied to a system that, by definition, contains everything. The Wheeler-DeWitt equation, derived by Bryce DeWitt in 1967 by applying canonical quantization to the constraints of general relativity, is the quantum mechanical equation of motion for the universe as a whole. It governs a wave function, usually denoted psi of the three-metric and matter fields, that is defined on the space of all possible three-dimensional geometries and matter configurations, called superspace. The Wheeler-DeWitt equation is a functional differential equation, and its solutions represent quantum states of the entire universe, including its geometry, matter content, and all physical processes within it. There is no external time variable in the Wheeler-DeWitt equation. Time is not a background parameter, but an emergent concept derived from the correlations between different degrees of freedom within the universe. The measurement problem in standard quantum mechanics arises because there is a quantum system being measured, a classical apparatus performing the measurement, and an observer outside the system interpreting the result. In quantum cosmology, there is no classical apparatus outside the system and no observer external to the universe. The entire measurement chain, from quantum system through apparatus to observer, is inside the wave function. The Copenhagen interpretation, which requires a classical realm outside the quantum system being described, is simply inapplicable. Something like the Everett interpretation is required. The wave function of the universe evolves according to the Wheeler-DeWitt equation, and observers within the universe are themselves quantum systems whose states are components of the total wave function. What any observer observes is their own branch of the universal wave function, and the appearance of definite outcomes follows from decoherence within the universe rather than from collapse imposed by something outside it. James Hartle and Stephen Hawking applied this framework in their no-boundary proposal of 1983, which specifies a particular quantum state for the universe as a whole, and derives from it predictions for the large-scale structure of the universe, including its spatial flatness and the near-scale invariant spectrum of primordial density perturbations. The no-boundary wave function is a specific solution to the Wheeler-DeWitt equation, chosen on the basis of a particular boundary condition. The universe has no boundary in imaginary time, meaning its quantum state is specified by a path integral over compact Euclidean 4 geometries. Whether this choice of boundary condition is the correct one, and whether the semi-classical approximation used to evaluate the path integral is valid, are questions that have been debated since 1983 and remain unresolved. But the framework itself, a quantum state for the universe evolving according to a quantum gravitational equation, with observers inside the system, is broadly Everettian, whether or not Hartle and Hawking identify it as such. The inflationary multiverse, the cosmological scenario discussed in the context of the flatness problem, in which an eternal inflationary process produces an infinite number of pocket universes, is a distinct and complementary source of parallel worlds to the many worlds branching. In the inflationary picture, different pocket universes are separated by vast distances, and by the expansion of the inflating background. and they may have different physical constants or different vacuum states depending on the string landscape. These are not branches of the same quantum wave function in the sense of Everett. They are separate causally disconnected regions of a classical inflationary spacetime. The many worlds branching occurs within each pocket universe, producing the quantum mechanical branching described by Everett. A complete physical theory of the kind implied by eternal inflation combined with quantum mechanics therefore produces a two-level multiverse. A classical level of causally disconnected pocket universes produced by inflation, and a quantum level of branching histories within each pocket universe produced by quantum mechanics. Max Tegmark has argued that these two levels, along with other levels arising from mathematical structure, form a hierarchy of multiverses, with the Everett branching as the most empirically grounded level because it is directly implied by the confirmed predictions of quantum mechanics. The cosmological application of the many worlds interpretation gives it a scope and significance that extends beyond the interpretation of laboratory experiments. If the wave function of the universe is real and evolves according to the Wheeler-DeWitt equation, then the branching structure of the universal wave function is the fundamental structure of reality, and the world we observe is one branch among an incomprehensibly vast number of equally real branches, all of them constituting together the complete quantum state of the universe. The measurement problem in this context is not a puzzle about laboratory experiments. It is a question about the relationship between the fundamental quantum state of reality and the specific classical-looking world any observer finds themselves in. The Everett interpretation's answer, that every observer is in every branch simultaneously through different versions of themselves, is the only consistent answer currently available within the framework of quantum cosmology. The consistency of the Everett interpretation with quantum cosmology has been developed most technically in the work of Jonathan Halliwell at Imperial College London, and in that of Murray Gell-Mann and James Hartle, whose decoherent histories framework provides a systematic method for identifying the set of quasi-classical histories that emerge from the universal wave function through decoherence. In Gell-Mann and Hartle's formulation, a set of histories is decoherent if the interference between different histories in the set is suppressed to below any specified threshold. The quasi-classical histories, the histories that look like the familiar classical world we observe, are those whose interference with each other is suppressed by the enormous decoherence that occurs when the relevant variables are coarse-grained to scales accessible to observers. The quasi-classical histories are not the only histories in the universal wave function. They are the histories whose structure makes it possible for observers to exist within them and to make consistent records of past events. The condition for an observer to exist within a history is itself a condition on the decoherence of that history. Observers require persistent records. Persistent records require stable environments. Stable environments require decoherence. The framework is self-consistent. Quasi-classical histories are the ones in which observers can exist, and observers exist in quasi-classical histories because those are the histories that decohere sufficiently to allow persistent structures. The objections that have not been answered. The many worlds interpretation has serious, technically sophisticated critics whose objections go beyond philosophical discomfort or unfamiliarity. Several of these objections remain genuinely unresolved, and any honest account of the interpretation status must engage with them rather than dismiss them as misunderstandings. The preferred basis problem is one of the oldest and most persistent. The wave function of a quantum system can be written as a superposition in any basis, spin up plus spin down in the spin basis, but a different superposition in a different basis obtained by rotating the spin measurement axis. Which basis defines the actual branches? In what sense is spin up plus spin down a physically meaningful branching rather than an arbitrary decomposition of the wave function? Decoherence provides a partial answer. The preferred basis for macroscopic systems is the pointer basis. the set of states that are stable under interaction with the environment. The pointer states are the classical-looking states, and the branches corresponding to different classical outcomes are the ones that emerge from decoherence. But the pointer basis is only approximately defined, depends on the details of the system-environment interaction, and does not give a sharp criterion for exactly when branching occurs. The branches are fuzzy, their number is not well defined, and the decomposition of the wave function into branches depends on an approximation whose validity is scale-dependent. Critics, including Adrian Kent, argue that this fuzziness makes the many worlds ontology insufficiently precise to count as a physical theory. The problem of probability for post-branching observers is distinct from the Born rule derivation discussed in Chapter 11. Even granting the decision-theoretic derivation of the Born rule for pre-branching bets, the question of what it means for a post-branching observer to have had a 50% chance of being in either branch is conceptually difficult. After the branching, there are two observers, each of whom has a definite outcome and each of whom knows which outcome they have. Neither of them is in a probabilistic state. Each is definitely in their branch. The probability that was calculated before the branching referred to a future state of affairs that in the many worlds picture involves the existence of two observers rather than the uncertain outcome of a single observer. Whether the decision-theoretic framework successfully bridges this conceptual gap, or whether it merely describes how a pre-branching agent should bet on post-branching outcomes without explaining what the probability means for the post-branching observers themselves, is disputed by philosophers of physics, including Hugh Price at Cambridge and David Albert at Columbia. The ontology of branches raises further difficulties. In the many worlds interpretation, branches are not present in the wave function as discrete, individually labelled objects. The wave function is a smooth function on configuration space, and the branches are regions of this function that have approximately decohered from each other. The number of branches at any moment is not a well-defined integer. The criterion for counting branches depends on a decoherence threshold that is chosen by convention rather than by any fundamental feature of the physics. Two physicists who set different decoherence thresholds will count different numbers of branches and potentially assign different weights to individual branches in their application of the Born rule. This arbitrariness in counting has no analogue in any other fundamental physical theory. The combination of these unresolved problems means that the many worlds interpretation, despite its theoretical elegance and the serious attention it has received from first-rate physicists, is not a finished theory. It is a program, an approach to the foundations of quantum mechanics that identifies a set of problems to be solved and provides a framework within which to solve them. Whether the remaining problems are genuinely solvable or whether they represent fundamental obstacles to the coherence of the interpretation is the central question of current research in quantum foundations. The honest position is that the program has made significant progress on some problems, has left others open, and has not definitively established that the many worlds interpretation is correct, is complete, or is preferable to all alternatives under every criterion that a physical theory should satisfy. How this connects to the fine-tuning problem, the many worlds interpretation and the fine-tuning problems of physics, including the flatness of the universe, the cosmological constant, and the values of the fundamental constants, are connected in ways that are philosophically significant and scientifically contested. The connection runs through the anthropic principle and the multiverse, and it raises the question of whether the many worlds branching provides a physical basis for the kind of ensemble reasoning that the anthropic principle requires. Fine-tuning problems have a common structure. A physical parameter takes a value that is extraordinarily special from the perspective of the full range of values it could in principle take, and that value is precisely what is required for the existence of observers. The cosmological constant is close enough to zero that galaxies, stars, and planets can form, but not exactly zero, and not large enough to prevent structure formation by overwhelming gravitational attraction before it begins. The ratio of the electromagnetic force to gravity is large enough that atoms are stable, but not so large that stars cannot ignite. The mass of the proton, relative to the electron, is in a range that allows stable nuclei. In each case, the question is why the parameter takes a value in the observer-compatible range, rather than one of the far larger set of values that would produce a universe with no observers. The standard anthropic response is that we are not surprised to find ourselves in a universe compatible with our existence, because we could only find ourselves in such a universe. This reasoning requires an ensemble of universes with different parameter values, so that there is a meaningful sense in which the parameter could have taken other values, and the universe we observe is one of many. The inflationary multiverse, the string landscape, and the Everett multiverse all provide such ensembles, though of different kinds and with different relationships to the parameter values in question. The Everett multiverse is generated by quantum branching and does not, by itself, produce variation in the fundamental constants. Within any single Everettian branch, the constants are fixed. What varies across Everettian branches is the outcomes of quantum measurements. This is enormously varied. Every quantum event that has ever occurred in the history of the universe has produced branching, so the number of distinct Everettian branches with different macroscopic histories is incomprehensibly vast. But the fundamental constants, if they are fixed by the quantum vacuum state of the universe, are the same in every branch. The Everett multiverse therefore does not by itself explain why the constants have observer-compatible values. The connection between the Everett multiverse and fine-tuning becomes substantive when it is combined with the inflationary multiverse. In eternal inflation, different pocket universes can realize different quantum vacuum states with different effective values of the fundamental constants. Within each pocket universe, quantum branching produces an Everett multiverse of histories with those constants. The complete picture is an ensemble of pocket universes with varying constants, each containing an Everett multiverse of quantum histories. Observers within this total ensemble will, by selection, find themselves in a pocket universe with constants compatible with their existence, and within that universe, in a quantum branch that produce the specific macroscopic history leading to them. The anthropic reasoning applies at the level of the pocket universe selection, and the Everett branching applies within each pocket universe. What the Everett interpretation specifically contributes to this picture is a principled reason to take the wave function of the universe seriously as a physical object, rather than as a computational tool. If the wave function is real, and if the universe's quantum state is given by the no-boundary wave function or some other cosmological quantum state, then the branching structure of that wave function is a physical fact about the universe, not an artifact of how we choose to calculate. The ensemble of Everett branches is not postulated as an additional structure to make anthropic reasoning work. It is a consequence of the Schrödinger equation applied to the universe as a whole. This makes the Everett multiverse the most physically grounded of the proposed ensembles for anthropic reasoning, because it follows from the most fundamental and best confirmed equation of physics, rather than from speculative cosmological scenarios. What would falsify the many worlds interpretation? The claim that the many worlds interpretation is unfalsifiable is sometimes made as if it were a decisive objection. The claim is not entirely correct, and the sense in which it is correct reveals something important about the structure of the interpretation and the nature of scientific testing more generally. Understanding what could falsify many worlds and what cannot requires distinguishing between the interpretation itself and the interpretations it competes with, and between the predictions they make in common and the predictions they might make differently. The many worlds interpretation would be falsified if quantum mechanics itself were falsified, because many worlds is precisely quantum mechanics without any additions. If an experiment found deviations from the predictions of the Schrödinger equation or the Born rule, this would undermine many worlds along with every other interpretation that accepts those predictions. The objective collapse models, which do modify the Schrödinger equation, are potentially falsifiable by experiments that demonstrate quantum coherence on mass scales, where the collapse models predict decoherence. If such experiments successfully demonstrate large mass quantum interference at scales above the GRW or Diocey-Penrose thresholds, the objective collapse models are falsified. Many worlds is not falsified by this result. It predicts exactly the same large mass interference as the unmodified Schrödinger equation. The result eliminates collapse-based alternatives and leaves many worlds, pilot wave theory, and Copenhagen's no-collapse variance as the surviving interpretations. More specifically, many worlds would be undermined if a compelling derivation of the Born rule from the Schrödinger equation turned out to be impossible in principle, establishing that the Born rule is a genuinely independent postulate that cannot emerge from the wave function structure. This would mean many worlds is necessarily incomplete. It cannot be the full theory of quantum mechanics because it cannot derive one of quantum mechanics' central predictive rules from its stated ingredients. The ongoing technical work on the decision-theoretic derivation is therefore directly relevant to the interpretation's viability as a complete theory. If the derivation is shown to be circular or otherwise invalid, and no alternative derivation is found, this constitutes a serious blow to the interpretation's claim to theoretical completeness. Many worlds would also be falsified, in a practical sense, if a different interpretation were shown to be more theoretically compelling by some criterion, whether that criterion is parsimony, predictive completeness, or derivation from more fundamental principles. This is not a standard empirical falsification, but it is the kind of theoretical competition that drives progress in physics. If the pilot wave interpretation were shown to be fully Lorentz covariant and consistent with quantum field theory in a way that makes all of its ontological commitments theoretically natural, this would strengthen the case for pilot wave theory and correspondingly weaken the default preference for many worlds. If objective collapse models were shown to follow from a compelling theory of quantum gravity, this would strengthen the case for collapse-based interpretations. What cannot falsify many worlds is any experiment that confirms the standard predictions of quantum mechanics, because all interpretations predict those outcomes. The many worlds interpretation is not falsified by the failure to directly observe other branches, because the interpretation predicts that other branches are unobservable from within any given branch. It is not falsified by the subjective experience of definite outcomes, because the interpretation predicts that every observer in every branch experiences definite outcomes. The unfalsifiability of the interpretation with respect to these specific experimental outcomes is not a weakness unique to many worlds. It is shared by every interpretation, because every interpretation is designed to reproduce the standard predictions. The implications become even more difficult once the double-slit experiment is connected to the modern theory of decoherence, which emerged in the late 20th century as physicists began analyzing how quantum systems interact with their environments. Decoherence demonstrated mathematically that quantum superpositions do not simply disappear when measurements occur. Instead, the quantum system becomes entangled with surrounding particles, radiation fields, and measuring devices, causing the different components of the wave function to lose the ability to interfere with one another. The interference pattern vanishes, not because one outcome is selected by magic, but because the environment itself begins carrying information about the system's state. This distinction matters enormously. In the classical picture, measurement reveals a pre-existing reality. In quantum mechanics, measurement physically alters the structure of the system by embedding information into the wider environment. Once this happens, the superposition evolves into effectively separate branches that no longer interact. From the perspective of an observer inside one branch, it appears as though a single outcome has been selected. But the underlying equations describing the total quantum system never eliminate the other possibilities. The Schrödinger equation continues evolving all components simultaneously. This is why many physicists argue that decoherence strengthened the many worlds interpretation rather than weakening it. Decoherence explains why quantum branches stop interfering and why observers experience apparently classical realities, but by itself it does not explain why only one outcome should exist. The mathematics still contains all outcomes. The wave function still evolves deterministically. No collapse appears anywhere in the formalism. To remove the unobserved branches requires adding an extra rule beyond the standard equations of quantum mechanics. The scale at which this becomes relevant is not limited to microscopic particles. Experiments over the past several decades have pushed quantum interference into increasingly large systems, including complex molecules containing hundreds and, in some cases, thousands of atoms. Quantum behavior has been demonstrated in superconducting circuits large enough to be visible under a microscope and in laboratory systems engineered to maintain coherent quantum states for measurable periods of time. Every increase in experimental scale has expanded the boundary at which quantum mechanics appears valid. The anticipated transition where reality would become definitively classical has never been found. This creates a deeply uncomfortable possibility. If quantum mechanics applies universally, then there may be no fundamental boundary separating microscopic quantum systems from macroscopic observers. Human beings, measuring devices, planets, stars and galaxies would all ultimately obey the same quantum laws. Under that assumption, the branching structure implied by the many worlds interpretation would not be confined to laboratories or isolated particles. It would apply to the entire universe continuously, at every interaction where alternative quantum outcomes become physically distinguishable. The unsettling aspect of this conclusion is not merely the existence of parallel branches, but the sheer inevitability with which the mathematics seems to produce them. The Schrödinger equation does not contain any mechanism that selects a preferred reality. It simply evolves quantum states forward in time with relentless consistency. The branching structure emerges naturally from the formalism itself once decoherence prevents interference between alternatives. In that sense, the many worlds interpretation is not an exotic addition to quantum mechanics. It is what remains when nothing is added beyond the equations that already work. Whether that picture is ultimately correct remains unknown. But the deeper point survives regardless of interpretation. The double-slit experiment revealed that reality at the quantum scale does not consist of objects possessing definite classical properties independent of interaction. The world described by modern physics is fundamentally probabilistic, relational, and dependent on the flow of information through physical systems. Whatever reality ultimately is, it is stranger than the classical universe human intuition evolved to understand. Another possible route to falsifying many worlds would emerge if future physics demonstrated that the quantum wave function itself is not an ontologically real object, but only a statistical tool encoding incomplete information about an underlying classical reality. Certain hidden variable approaches attempt to move in this direction, though Bell's theorem and the experimental violations of Bell inequalities have already eliminated large classes of local hidden variable theories. Any future framework capable of restoring a fundamentally classical ontology while reproducing all verified quantum predictions would substantially weaken the motivation for many worlds, because the interpretation depends on treating the wave function as physically real rather than merely epistemic. The problem is that modern quantum experiments have consistently pushed physics in the opposite direction. Bell tests, delayed choice experiments, quantum eraser setups, and increasingly sophisticated entanglement measurements have repeatedly strengthened the conclusion that quantum states cannot easily be understood as reflections of hidden classical properties existing prior to measurement. The more precisely these experiments are performed, the more difficult it becomes to preserve an intuitive picture of localized objects carrying definite states independent of interaction. This has gradually shifted the debate surrounding many worlds away from the question of whether the interpretation is absurd and toward the question of whether the alternatives are actually any less absurd. The Copenhagen interpretation avoids explicit parallel worlds, but does so by introducing an undefined measurement process that separates the quantum and classical domains without specifying exactly where that boundary exists. Objective collapse theories preserve a single classical reality, but at the cost of modifying quantum mechanics with additional mechanisms that remain experimentally unconfirmed. Pilot wave theory restores determinism, but requires fundamentally non-local hidden variables and an underlying structure that becomes increasingly difficult to reconcile with relativistic quantum field theory. In this sense, the persistence of many worlds within modern physics is not primarily driven by a fascination with science fiction concepts of alternate universes. It persists because the interpretation follows directly from taking the mathematical formalism of quantum mechanics seriously without introducing additional postulates. The Schrödinger equation evolves smoothly, deterministically, and universally. If that equation applies to all physical systems, including observers and measuring devices, then branching emerges naturally through decoherence. The existence of multiple branches is not inserted artificially into the theory. It is the consequence of refusing to insert anything else. There is also a deeper reason the interpretation continues to matter in modern theoretical physics. Quantum cosmology attempts to apply quantum mechanics not merely to particles inside the universe, but to the universe as a whole. In that context, the Copenhagen interpretation becomes conceptually unstable because it relies on external observers and measurements, while the universe, by definition, contains everything physical. Many worlds avoids this issue because it does not require an observer outside the system. The universal wave function evolves according to the same equations everywhere, at all scales, without requiring collapse from outside the formalism. Whether this picture ultimately describes reality remains unknown. But the scientific status of many worlds is often misunderstood. The interpretation is not a speculative fantasy disconnected from physics. It is one possible answer to a problem created by experiments whose results are among the most rigorously verified in science. The question is not whether quantum mechanics works. It does. The question is, what kind of reality could produce mathematics that works this well while describing a world so radically unlike the one human intuition expects? The debate between interpretations is not primarily empirical. It is a debate about which ontology is most coherent, most complete, and most consistent with the full structure of physics, including quantum mechanics, general relativity, and quantum cosmology, what the experiment actually proved and what it did not. The double-slit experiment, in all its versions and variants, proves something specific and something more general than is usually stated. The specific thing it proved is that quantum systems in superposition states exhibit interference that disappears precisely when which path information becomes available, regardless of whether that information is ever observed by any conscious entity. The physical pattern on the screen depends on the physical existence of information in the world, not on the subjective awareness of any observer. This is not a philosophical interpretation. It is a measured fact confirmed by every version of the experiment ever performed. What this specific fact implies about reality is where the interpretation becomes unavoidable. The most direct reading of the data is that quantum systems exist in superpositions of multiple states simultaneously, that these superpositions are physically real in the sense that they have physical consequences, and that the interference between superposition components is a physical process that can be made to appear or disappear by physical changes to the world that determine whether information about the system's state exists anywhere. The information that matters is not in any mind. It is in the physical correlations between the quantum system and everything else in the universe that has interacted with it. The double-slit experiment did not prove that the many worlds interpretation is correct. No experiment currently can do that, in the sense of ruling out all competing interpretations. What it proved is that the standard classical picture of particles with definite trajectories through one slit or the other is wrong. That the interference pattern requires each particle to be in a superposition that spans both slits simultaneously, and that the resolution of that superposition into a definite detection event is connected in a precise and reproducible way to the physical existence of which path information in the world. The experiment does not tell you what happens to the other component of the superposition when the particle is detected. It does not tell you whether the other component vanishes, whether it persists in some form, or whether it constitutes a real physical history that some other version of the universe pursues. The many worlds interpretation answers these questions in the most direct way available. The other components of the superposition do not vanish. They persist as real physical histories, decohered from the history we observe, evolving according to the Schrödinger equation. The experiment that showed each particle passes through both slits at once, in the sense that both paths contribute to the interference, is consistent with a picture in which both paths lead to real outcomes in real branches. The particle does not choose one slit, it goes through both. The outcomes do not select one result, they both occur. The double-slit experiment, taken at full face value without any additional postulate that eliminates one component of the superposition, implies that reality branches at every quantum event. This is the sense in which the title of this script is more than rhetorical. The double-slit experiment did not prove that parallel worlds exist in the way that a physics experiment proves the charge of the electron or the mass of the Higgs boson. It proved something more foundational and more disturbing, that the classical picture of a single world with definite histories is wrong, and that the correct quantum mechanical description requires superpositions whose full physical significance cannot be accounted for without committing to more than one classical history. Whether those multiple histories are real worlds in the sense of the many worlds interpretation, or whether they are something else, whether they are mere mathematical possibilities that collapse to a single actuality, whether they represent different aspects of a complementary description without independent existence, depends on which additional postulates you are willing to add to the Schrödinger equation and how you justify them. The many worlds interpretation adds none. It accepts all the consequences. The price it pays is the metaphysical extravagance of an inconceivably large reality, most of which is permanently inaccessible to any observer within any branch. The price the Copenhagen interpretation pays is a theory with unspecified classical quantum boundary, an undefined notion of measurement, and a prohibition on asking what is happening between observations. The price the objective collapse models pay is a modification to the Schrödinger equation that has not been derived from any more fundamental theory and that has not yet been confirmed experimentally. Every interpretation of quantum mechanics pays a price. The question is which price is worth paying, and the answer depends on what you think physics is for. If physics is for making predictions, Copenhagen suffices. If physics is for describing what is happening, something more is required. The double-slit experiment showed that what is happening at the quantum scale is not what classical intuition expects. Every attempt to say more precisely what is happening has led to one version or another of parallel realities. Not because physicists have a romantic attachment to the idea, but because the mathematics that has been confirmed to 11 decimal places, taken seriously as a description of the world, produces them as a consequence. The implications become even more difficult once the double-slit experiment is connected to the modern theory of decoherence, which emerged in the late 20th century as physicists began analyzing how quantum systems interact with their environments. Decoherence demonstrated mathematically that quantum superpositions do not simply disappear when measurements occur. Instead, the quantum system becomes entangled with surrounding particles, radiation fields, and measuring devices, causing the different components of the wave function to lose the ability to interfere with one another. The interference pattern vanishes not because one outcome is selected by magic, but because the environment itself begins carrying information about the system's state. This distinction matters enormously. In the classical picture, measurement reveals a pre-existing reality. In quantum mechanics, measurement physically alters the structure of the system by embedding information into the wider environment. Once this happens, the superposition evolves into effectively separate branches that no longer interact. From the perspective of an observer inside one branch, it appears as though a single outcome has been selected. But the underlying equations describing the total quantum system never eliminate the other possibilities. The Schrödinger equation continues evolving all components simultaneously. This is why many physicists argue that decoherence strengthens the many worlds interpretation rather than weakening it. Decoherence explains why quantum branches stop interfering and why observers experience apparently classical realities, but by itself, it does not explain why only one outcome should exist. The mathematics still contains all outcomes. The wave function still evolves deterministically. No collapse appears anywhere in the formalism. To remove the unobserved branches requires adding an extra rule beyond the standard equations of quantum mechanics. The scale at which this becomes relevant is not limited to microscopic particles. Experiments over the past several decades have pushed quantum interference into increasingly large systems, including complex molecules containing hundreds, and in some cases, thousands of atoms. Quantum behavior has been demonstrated in superconducting circuits large enough to be visible under a microscope, and in laboratory systems engineered to maintain coherent quantum states for measurable periods of time. Every increase in experimental scale has expanded the boundary at which quantum mechanics appears valid. The anticipated transition, where reality would become definitively classical, has never been found. This creates a deeply uncomfortable possibility. If quantum mechanics applies universally, then there may be no fundamental boundary separating microscopic quantum systems from macroscopic observers. Human beings, measuring devices, planets, stars, and galaxies would all ultimately obey the same quantum laws. Under that assumption, the branching structure implied by the many worlds interpretation would not be confined to laboratories or isolated particles. It would apply to the entire universe continuously, at every interaction where alternative quantum outcomes become physically distinguishable. The unsettling aspect of this conclusion is not merely the existence of parallel branches, but the sheer inevitability with which the mathematics seems to produce them. The Schrödinger equation does not contain any mechanism that selects a preferred reality. It simply evolves quantum states forward in time with relentless consistency. The branching structure emerges naturally from the formalism itself once decoherence prevents interference between alternatives. In that sense, the many worlds interpretation is not an exotic addition to quantum mechanics. It is what remains when nothing is added beyond the equations that already work. Whether that picture is ultimately correct remains unknown. But the deeper point survives regardless of interpretation. The double-slit experiment revealed that reality at the quantum scale does not consist of objects possessing definite classical properties independent of interaction. The world described by modern physics is fundamentally probabilistic, relational, and dependent on the flow of information through physical systems. Whatever reality ultimately is, it is stranger than the classical universe human intuition evolved to understand. The double-slit experiment and the quantum reality problem. The double-slit experiment is simple enough to be demonstrated in a high school classroom and deep enough to have occupied the most capable physicists in the world for a century without resolution. Its results are beyond dispute. Its implications are not. The interference pattern that appears when which path information is unavailable and disappears when it is a physical fact that constrains every theory of reality at the quantum scale. The quantum formalism that correctly predicts this pattern with extraordinary precision contains, when its mathematics is taken seriously, a description of reality that is either incomplete, supplemented by collapse dynamics that have never been derived or confirmed, or committed to an inconceivably vast structure of parallel worlds. Hugh Everett's contribution was to notice that the Schrödinger equation, applied without modification to the full system of particle plus apparatus plus observer, produces the branching structure automatically. No collapse is needed. No undefined boundary between quantum and classical is required. The price is that the world we observe is one branch among an enormous number of equally real branches, and that every quantum event is simultaneously producing histories we will never experience. The technical program of making this interpretation precise, of deriving the Born rule within it, of specifying what a branch is, and of connecting it to the full structure of quantum field theory and quantum cosmology, is ongoing and incomplete. But the motivation for taking it seriously, the simplicity of adding nothing to the Schrödinger equation rather than adding collapse dynamics that cannot be derived, has never been stronger. What the experiment actually proved is that reality at the quantum scale is not the reality of common sense. The particle went through both slits. The measurement result was not determined before it was measured. The information about which path was taken, existing in physical correlations between the particle and the detector, determines what pattern appears on the screen, without any conscious observer needing to inspect it. These facts are confirmed. Their interpretation is not. And the interpretation that requires the least supplementary machinery beyond the equation that has been confirmed to 11 decimal places is the one in which both slits lead to real outcomes. All measurement results occur, and the universe we inhabit is one of a branching infinity of equally real worlds.